Okay, this is the first of a few different videos that I'm putting together as to how to integrate trigonometric integrals. A lot of them require some tricks regarding algebra as well as some of the trig identities. So what I figured I'd start with are some of the most basic types with the sines and the cosines. Okay, and these are probably the ones that you'll see a little bit later in the course when we start doing some things like our trigonometric integrals or our trigonometric substitutions rather. So one of the first techniques that we always see is, let's say we have an integral that combines both the sines and the cosines within them. Okay? Here's what I always try to do. I always pick one, if I'm going to reduce a power, I'm going to pick on the one that's smaller already. So in this case, let's pick on this cos cubed. All right? And I'm going to show you what I'm going to do with this. I'm going to rewrite this as sine to the fourth x. And instead of cos cubed, I'm going to write this as cos square x times cos x dx. Okay. Now the reason I do that is because I know that there's a Pythagorean identity to where I can rewrite this cosine and try to get it in terms of sine. So let's do that. Let's now rewrite this. And we're going to say that this now becomes the integral sine to the fourth x. Instead of cos squared, remember that cos squared has the Pythagorean identity 1 minus sine square x. And then this cos x dx, I'm not going to operate on. All right. At this point, even though it might not be easy to see, this actually becomes a u substitution problem. So some of the techniques that we learned earlier, for instance, the u substitution, the integration by parts, they're not going to go away. In fact, we have to make sure we have a good foundation of those to be able to do these types. Let's let u be equal to just regular old sine x. The reason I do that is because I know the derivative of sine gives me the cosine x dx. So my du is going to be cos x dx. And hopefully now you can see that the substitution gets rid of the cos x dx, but also gets the sines in terms of u. So my new integral, since sine is u to the fourth would be sine to the fourth. Along the same lines, 1 minus u squared. And then finally, cos x dx is our du. At this point, we want to distribute the u to the fourth, so let's go ahead and do that. So now we get an integral of quantity u to the fourth minus u to the sixth du. And finally, we can integrate those two terms. They integrate very nicely. Okay. So by integration, we add 1, divide by the new exponent, so we get u to the fifth over 5, minus u to the seventh over 7 plus c. And then finally, we can put this back in terms of x rather than u. So I believe that for an answer, and I'm just writing it up a little bit so we can see, I'm going to say this becomes sine to the fifth of x over 5 minus, instead of u to the seventh, sine to the seventh x over 7. And of course we have our constant of integration c that we're just going to bring over. So we're going to have our plus c. So hopefully you guys can see that it's not that difficult. Okay? We just have to make sure that we use the Pythagorean identity, and we also use a little bit of exponentation to help us out with this one. A different technique is utilized for the sine square of x dx. If you try to use the Pythagorean identity, let's just go ahead and do it just to say that we tried it. Okay? By Pythagorean identity, this would become integral of 1 minus cos square x dx quantity, 1 minus cos square x. Now the 1 is very easy to integrate. That just becomes x. However, cos squared leads us into the same problem of sine squared. We'd have to use another Pythagorean identity, which would actually just get it back to the original integral. So unfortunately, in this example, Pythagorean theorem, or excuse me, Pythagorean identity is not the way to go with this one. However, a good technique to use is something called the power reducing formula. There's a formula that hopefully you guys remember from either trigonometry or pre-calculus that says the sine squared is really the same as 1 minus cosine of 2x divided by 2 dx. Usually, when you have a singular trigonometric function and you have an even power, this is the way to go about it. Okay? Now, it gets more difficult if you start doing fourths and sixth powers. Okay? They just become tedious. This one's not too bad. I'm going to factor out the 1/2 and turn it into two different integrals, because then you might be able to see how easy it is after that. So factoring out the 1/2, I get 1/2 integral of 1 dx minus 1/2 integral of cos 2x dx. Okay? So hopefully you see what I did there. I factored out the 1/2, and then I split it into two different integrals by the minus sign. Notice the 1 went away because 1 times dx is just dx. All right. Now, this guy, extremely easy to evaluate. Antiderivative of dx is just x. So this now just becomes 1/2 x. Okay, that's easy. Unfortunately, this is not a basic integral. The second is a u substitution problem because we have something inside of another function. Okay, so let's do this. Let's let u be equal to 2x du is going to be 2 dx, which is good news because that gives us u. This gives us du. The only thing we don't like is the 2 that's in front of the dx. Let's divide both sides by 2. So now, again, I always just focus on the harder integral, and then I just leave the rest of the stuff, as we saw before in the videos with the integration by parts. I get minus 1/2 integral cos u, and then instead of dx, dx is the same as du over 2. Okay, so these 2's go away, and du over 2 is dx. I can factor out this 1/2, and I can get minus 1/4. So I get minus 1/4 integral cos u du. And now we finally start to see that this is valuable in maybe 2 or 3 more steps. Okay? So let's go back up here and just write everything that we have. We have our 1/2 x. The antiderivative of cos is sine. So I get 1/2 x minus 1/4 sine of u plus c. And let me erase this integral. We'll put it back up in a second. I'll just erase this too so it's not so scrunched up in there. So 1/4 sine of u plus c. And then finally, we just back substitute. So we know that when we back substitute for u, we said that u is 2x. So ultimately, we end up with 1/2 x minus 1/4 sine of 2x plus c. Okay, and that's our answer for our second integral. All right. So again, the trick is that if you have an even power and a trig function completely by itself for sines and cosines, you use this power reducing formula. Okay, you're going to see this one a lot. Okay. All right, another integral that I had on the board that I erased was the integral of cos cube x dx. Unfortunately, there's no power reducing for a cubic. Okay? So let's try this. Let's go ahead and see what happens if you have an odd power, or a sine and cosine. And this actually is a little bit easier because it sort of resembles what we did in the first example. Let's split off a cosine. So this is going to now be the integral of cos square x times cos x dx. So just split off one of the factors of cosine. I'm also going to now use the Pythagorean theorem, or the Pythagorean identity for this one. Okay? And again, the reason we don't use the power reducing is because there's more than one trig function going on here. And when I say that, more than one trig factor, if you will. Now, if it was just cos squared, then you would use the power reducing. Okay? This would turn into a plus instead of a minus. Okay? So let's use the Pythagorean identity. This now becomes the integral of 1 minus sine squared x. And then we still have our cos x dx. All right. Hopefully it's obvious to see that this is a u substitution, just like the problem that we had a few moments ago. Okay, let's go ahead and do the substitution. It looks like that u should be sine x, just like it was a moment ago. Okay, so I'm just going to draw an arrow down here. That let's let u be equal to the sine of x, and our du is going to be equal to cos x dx, which is good news because that's exactly what we have left over. No need to divide, no need to multiply by any coefficients. So now our integral in terms of u is now 1 minus u squared du. All right. And at this point, this is a really basic integral. We evaluate, we back substitute. Antiderivative of 1 is going to be u, since we're integrating with respect to u. Antiderivative of u squared is u cubed over 3. We need our plus c. And then finally, we just back substitute for u. We already said that u was sine, so I believe we would end up with a sine x minus sine cubed x over 3 plus c. All right. So hopefully these three basic examples will give you a head start as to being able how the techniques for evaluating these sorts of structures, if you would. And when I say structure, I mean a sine and a cos kind of melded together, one with a lower power, one with a higher power. Another example is when you just have an even power and a trig function by itself. Another example is when you have a trig function by itself, a sine or cosine, and an odd power. Okay? So maybe take a note of how to attack each of these, and then rewatch it a few times to be able to see like the algebra and the trigonometry involved with this.